Okay, in this chapter we're going to talk about exponential, logarithmic, and transcendental functions. And so here I'm just going to give you a quick review about exponential functions. First of all, an exponential function is defined where a is greater than 0 but not equal to 1. It's defined as f of x equals a to the x, where the domain is all real numbers and the range is positive real numbers. Here are a few examples of exponential functions. Make sure you remember your properties of exponents, which I'm not going to cover these because if you're in calculus you should know these properties, but if you need to you can freeze the video and look at my examples for properties of exponents and then restart it when you're ready to continue. These are graphs of two basic exponential functions. The graph on the left would be the graph of y equal a to the x, where the base is between 0 and 1, like 1/3 to the x. The graph on the right is where the base is greater than 1, like y equal 3 to the x. And you can see that the graph on the left, the domain is all real numbers. Well, actually both of these graphs have basically the same traits, except for one's always decreasing and one's always increasing. And then the limits are different. As x approaches infinity, this one goes to 0, whereas x approaches infinity, this one goes to infinity. And here, as x approaches negative infinity, this one goes to infinity. And then here, as this one approaches negative infinity, this one goes to 0. And then, of course, they're both continuous and one-to-one. So if you wanted to graph exponential functions, basically you could graph them the same way you graph any other function. You just plug in values for x and then get the corresponding y values. So if I wanted to graph this function, I could just plug in -2, -1, 0, 1, and 2 and get the corresponding y values. At -2 I get a fourth, at -1 I get a half, at 0 I get 1, at 1 I get 2, at 2 I get 4, and then just plot the values. And if I wanted to graph 1/4 of the negative x, I could evaluate that at these values. But you can see here I can only get 3 of them to fit on the grid. So when x is -1, I get 4. When x is 0, I get 1. And then when x is 1, I get 1/4. So you can evaluate that. They all have basically the same general shape, and the base determines the rate of increase or decrease. Alright, so e is a commonly used value in calculus. It's similar to pi in that it's an irrational number. The value actually can be derived from either of the following limits. The limit of 1 plus x raised to the 1 over x as x approaches 0 actually is e. Or you could say the limit of 1 plus 1 over x raised to the x as x approaches infinity is actually equal to e. 2.7, 2.71, 2.71828, and so forth are approximations of e, but e itself is just e. So the exact value of e is just e. Now if you wanted to graph the function e to the x, well, you could do a table. Like if x is -2, you could grab your calculator and figure out what is e to the -2, and it's about a tenth, a little more than a tenth. E to the -1 is 0.37, so a little more than a third. E to the 0 is 1. E to the first is just e, which is about 2.72. And then e squared is about 7.4, which would be way up here somewhere. So you can graph it that way. There's two types of growth models that you can run into. One's an exponential growth model, and this one tends to increase without bound as x increases. And another model is called the logistic growth model, and it actually has a horizontal asymptote. So it starts to increase, but then it levels off. So that's called the logistic growth model. And so one model might represent a population growth where there's nothing that's slowing down the population growth, but this might represent a population growth where after so much time maybe there's not enough food or resources to support large populations, so the population levels off. You can use the exponential function p times 1 plus r over n to the nt to calculate compound interest. But if you wanted continuous compounding, this would be a formula for when you have like a certain number of compounding periods per year. So like if you had, if you were compounding monthly, n would be 12. If you compounded daily, n would be 365. But if you wanted to compound continuously, then you've got to let n go to infinity. And so here I'm going to show you what would happen. Now remember about this limit I gave you earlier. Well, if you took the limit of that compound interest function as it should say n goes to infinity. Everywhere you see an x, it should say n. So actually you could factor the p out and you get 1 plus r over n to the nt as n goes to infinity. Okay, but nt can be written as n over r times rt. You can check that. That actually equals nt. And again, that should be n right there. And now let's see. So what I can do is, using properties of exponents, I can actually write this as 1 plus r over n to the n over r raised to the rt. And then if I let x be r over n, then 1 over x would be n over r. So if I let x be r over n, then I can convert this. This becomes x, and then n over r becomes 1 over x, and then rt is still out here on the outside. So this limit, so now I get the limit as x approaches 0 of 1 plus x to the 1 over x in here, and that limit is actually e, so that I'm going to have e to this rt power out here, and then with a factor of p, and that gives me the continuous compounding formula for when the number of compounding periods goes to infinity. So there's the formula there. Okay, now if you want to do some examples here, it says $5,000 is invested at an annual rate 3.9% for a period of 20 years. If money is compounded annually, what will the balance be after 20 years? Well, for annual compounding, I use that first formula up there. So n will be 1, since it's compounded once a year. So I'd have 5,000 times 1 plus 0.039 over 1 times 1 to the 20th. And then I got that value. The second one says, what if we compound monthly? Well, if we compound monthly, then you have to replace the 1 with 12 here and up here. So you have 5,000 times this expression to the 240th power, which gives you this number. And then if you compound continuously, then you have to use this formula here, p times e to the rt, and you get 5,000 e to the 0.039 times 20, which is 10,907.36. Okay, so that was the review of exponential functions. Now I'm going to talk about log functions. Here's the definition of a logarithm. It says for a is greater than 0, a is not equal 1. When you see y equal log of x base a, that's equivalent to saying x equals a to the y. The domain of your log function is all real numbers, and the range is, the domain is positive real numbers, and the range is all real numbers. So to understand logs, one of the things you might want to do is be able to write the log in exponential form. So log form and exponential form looks kind of like this. To convert exponential form to log form and log form to exponential form, I just realized I don't have the actual relationship on here, so let me give it to you. Okay, so these two expressions mean the same thing. If you have the log of x base a equal to y, that's the same as saying a to the y equal x. So if I wanted to convert 2 to the 4th equals 16, which is a true statement in log form, I'd write it as 4, the exponent, is equal to the log of 16 base 2. And that's how you would do that. If 3 to the negative 2 equal 1/9 would convert to this, the exponent negative 2 is equal to the log of 1/9 base 3. And you can look at the others. If you wanted to go the other way, if you wanted to convert a log into exponential form, here 4 equals log of 81 base 3 would be the same as saying 3 to the 4th is equal to 81, and then negative 5 equals log of 132 base 2 is the same as saying 2 to the negative 5 equals 1 over 32. Alright, you can read the other one there. Okay, the natural log function is actually ln of x, and so the natural log function, y equals natural log of x only if and only if e to the y equal x, and that goes back to that relationship I just showed you, but for the base e. So if you wanted to graph the natural log function, you could actually graph it by plugging in y values and get the x values. So let's plug in y values. So let's say you wanted to graph, let's do log of x base 2 first. Let's say you wanted to graph that. Well, that's the same as x equal 2 to the y. So if you plug in y values, you know, x equal negative 2, you get a fourth, negative 1, you get a half, y equals 0, you get 1, y equal 1, you get 2, y equal 2, you get 4. So now if you plot those points, 1/4, negative 2, 1/2, negative 1, 1, 0, 2, 1, 4, 2, you'll see the graph. And so there's the graph of log of x base 2. And now if you want to do it for e to the y equals natural log of x, you have to graph x equals e to the y. So plug in y values of negative 2, negative 1, 0, 1, and 2, and then see what their values are on the calculator, and then just plot them on the grid, and you can plot them here. You can label them. I didn't label them here, but that's basically what the natural log of x is going to look like. Now the natural log of x, or the log functions and the exponential functions, are actually inverses of one another. Here's the exponential function 2 to the x, and here's the log of x base 2. And so you'll see their reflections about the line y equal x, and that's one of the qualities of inverses. The common log, y equal log of x, is just the base 10 logarithm. So, you know, log of 10 base 10 is 1, log of 100 base 10 is 2, and so forth, because that's just the base 10 logarithm. So the natural logarithm is like this, and it's base e, and the common log, it looks like this, and it's base 10. Okay, now this section doesn't cover applications, but logs are used in many areas: earthquake intensity, sound intensity, chemical pH balance, gross models, and so on. Let me just give you some common properties of log functions, and then I'll go over the actual properties of logarithms in the next video. For all positive real numbers a not equal to 1, the function f of x equal log of x base a has the following properties. The domain is the set of positive real numbers 0 to infinity. The range is from negative infinity to infinity. And then the x-intercept would be 1, 0. The y-axis would be the vertical asymptote. And then f of x is an increasing function if a is greater than 1, and it's a decreasing function if a is between 0 and 1. And then also f is a one-to-one function. So as I said, I'll finish up log functions on the next video.